Welcome to lecture 39 of the course on high performance computing. The previous lecture we started looking at parallel architecture. Our objective is to understand a little bit more about the programming of parallel machines, because parallel machines are fairly widespread today. They provide improved performance. Programs run on parallel machines can run much faster. They also provide the possibility of fault tolerance, which is sometimes an important requirement. Now, in looking at the possibility of a parallel machine in which the many processors actually share a single physical address space with a single shared memory, in the previous class we understood that there is a potential problem if each of the processors has a cache, and this was referred to as the cache coherence problem, which we looked at from an example of understanding what happens when a simple program which has two processes runs on a parallel machine in which there are four processors, in which each of them has a cache. Each of the processors has a cache. And in the example which we went through, you'll notice that there was a parallel program running as two processes, process P1 and process P2. They have a shared variable called x. X is initially equal to 0, which is in the main memory. Now, when process P1 reads x, a copy of the variable x comes into the cache of the processor running process P1. If the slides were shown, then they could see what was being said. Then subsequently, if process P1 reads x again, it will get the value of x out of its cache. Now, the problem is, of course, that process P2 could be sharing the variable x, and therefore if process P2 also reads x, then copy of x will come into its cache. Subsequently, process P2 could read the value of x again and again. But if now process P1 or process P2 for that example was to modify the value of the variable x by ordinary x equal to 1, or some kind of a store instruction on the memory variable x, the effect would be that the other cached copies of x could become incorrect, and therefore if process P2 actually read the variable of x again, it would get the old invalid value of x equal to 0, whereas currently from the perspective of the parallel program, x is equal to 1. This is a serious problem because the correct operation of the program has been compromised, and it's referred to as the cache coherence problem, which we described in the next slide. So if the cache coherence problem arose if there is a shared memory parallel machine in which each of the processors has a cache, and the problem arises, it's a data consistency problem, it arises when there's the need to modify a shared variable. It gets modified in a cache, but maybe not in all the caches, and this has to be handled. It cannot just be left to the programmer to deal with, because it's not possible for the programmer to deal with correction of the incorrect values inside caches. Therefore, either the hardware or the system software has to handle this. We looked at one simple mechanism which could be built into shared memory parallel machines in which there are snooping cache controllers. In other words, in which the cache controller at each of the processors is constantly monitoring what is being done on the shared bus by it and by other processors. So if this is the case, then whenever there's an update of some kind which has happened, or an update to main memory which happens on the shared bus, each of the cache controllers will notice this and can take corrective action, possibly by updating or invalidating its copy of the cache block in question. And we saw that this could correct the problem with the previous example, because now when process P1 reads x and gets a copy of the block containing x in its cache, it doesn't matter if process P2 gets a copy in its cache. Subsequently, when process P1 modifies the value of x, under the write once protocol, the copy in its cache will get updated to 1, the copy in the main memory will get updated to 1. The activity of updating main memory will require a shared bus transaction, which will be observed by all the caches in the system, since their cache controllers are snooping, and therefore each of the other caches in the system, cache controllers could invalidate their copies of the block, as shown in the next step, so that if any of the other processes then read the value of x, it would get a cache miss, which is correct behavior, as opposed to the previous situation where it actually read the wrong value of x equal to 0. Okay, now this is a simple idea which can result in the correct execution of programs, but it may not result in good performance for the execution of those programs, as we will realize if we think about what would happen in a shared memory system which uses something like the write once protocol, a Snoopy cache coherence protocol, but also uses locks to implement mutual exclusion of access to shared variables. You will remember that when we talked about concurrent programming, when we were talking about how the operating system shares the CPU among the different processes, we used this idea of a lock, which was a software mechanism built using special instructions such as a atomic read, modify, write instruction like test and set. But the lock is required so that in regions of a concurrent program or a parallel program where accesses to shared variables are going to take place, it might be important to ensure that at any given point in time only one process of the parallel program is modifying the shared variable at a time. So that requirement is still going to be present in parallel programming if one is using shared variables, and therefore just like one was using locks to ensure mutual exclusive access to shared variables in a concurrent programming, one would use locks to have mutually exclusive access to shared variables in a parallel program as well. The same concept carries through. Therefore, in thinking about the Snoopy cache coherence protocol, it doesn't hurt to also remember that the processes P1 and P2 that we just talked about will in all likelihood be using locks to ensure mutual exclusion in their access to the variable x. So let's now concentrate on the accesses to the locks themselves. So I'm showing you the same system that we had before. There are 4 processors and we have a parallel program running, but instead of just worrying about the accesses to the shared variables, let's concentrate on what happens to a lock. So let's suppose that the value of the lock is initially 0. You'll remember that our understanding of locks is, let me just remind you about locks. We're assuming that a lock is some kind of a shared variable which has a value of 0 if the lock is available and has a value of 1 if the lock is not available. Further, there are two functions which are provided for manipulating locks. One is a function which can be used to acquire the lock, and the other is a function which can be used to release the lock. So if there is a lock called L, a parallel program would, before any of its critical sections, would include a call to acquire lock, and at the end of the critical section would include a call to release lock, and the process would not be allowed to enter the critical section until the lock had been acquired. So the implementation of release lock was fairly simple. A process just had to set L equal to 0, indicating that the lock is now available. In implementing acquire lock, we used a special instruction which is available. There could be different variants on the instruction, but we were using the variant in which there's the instruction called test and set. So the idea of the implementation of acquired lock was the process wishing to acquire the lock would execute a while loop in which each time through the loop it would test and set the lock variable. The property of test and set is that it is an atomic instruction which will indivisibly do 3 steps as if they are one step. And the first step is to read the old value of L, the second is to modify L to 1 and modify the variable, the memory variable containing the lock L. So the net effect is that as long as the process executing acquire lock gets a return value of 1, in other words the lock is not available, it will continue executing this while loop. But as soon as the value of L becomes equal to 0, because another process has released the lock, then it will get a return value of 0 from test and set of L, and hence might be able to escape from the acquire lock. So this was how we talked about the implementation of a lock. And in terms of the parallel program, once again we assume that the same kind of a lock could be used. So if there is a situation where there is a lock variable which is initially equal to 0, let's suppose that a process running on the leftmost processor initially tries to acquire the lock by executing the test and set instruction. Since the value of the lock variable is equal to 0, which means that the lock is available, this process which executes test and set of L will successfully get a return value of 0 and escape from the test and set L loop within its acquire lock function, and therefore it will acquire the lock setting L to 1. So when it sets L to 1, the cached copy of L gets set equal to 1 and the main memory copy of L also gets set equal to 1. Now let us suppose that while this process on the leftmost process, the process running on the leftmost processor is now executing inside its critical section. Let's suppose that a process running from the same program, now running on one of the other processors, tries to acquire the lock. So while the process in the leftmost processor is holding the lock and inside its critical section, let's suppose that a process running on the second processor attempts to do a test and set of L. What happens when it executes test and set of L? In order to test L, it has to have a cache copy of the lock variable. So it gets a copy of L into its cache, and you'll notice that it tests L, sees that the value of L is equal to 1, and then indivisibly as the same operation sets L equal to 1. which is why the cached copy inside the leftmost processor suddenly disappeared. Now let me just repeat this once to make sure it's clearly understood. When the test and set L instruction is executed on the second processor, there will be a cache miss, and therefore a copy of the cache of the variable L will be brought to the block containing the cache containing of that particular processor. But indivisibly it is going to set L to 1, and that is going to be a modification of L, and therefore under the cache coherence protocol the main memory copy will also get set to 1, and because there is a bus activity, the cache copy inside the other processor will get invalidated, flushed, which is why we now have a situation that looks like this. So when the process on the second processor executed test and set of L, it caused the copy of the lock in the other cache to get invalidated, but it itself did not get the lock, because remember that the return value from the execution of test and set of L on the second processor was that the value of L is equal to 1. L is not available, and therefore it was not successful. Now let's suppose that at this point a process running on the third processor executes test and set of L. Once again it will suffer a cache miss, it will bring a copy of L into its cache, it will then set L indivisibly as part of the same operation, and the net effect is going to be that the main memory copy gets updated by an activity on the bus, and the cached copy in the second processor gets invalidated. Now there is one valid copy of the cache block containing the lock L, but that is in the third processor. Now as you can see, when any one of the processes executing on any of the processors executes test and set of L, for example now a process running on the fourth processor executes test and set of L, something very similar is going to happen. The cache copy inside the third processor will get invalidated because of the update of the main memory copy of the lock L inside due to the test and set instruction being executed. In effect, what's going to happen is the lock variable is going to move from cache to cache among all the different processors which have a process trying to acquire the lock. Ultimately, of course, the process which was executing in the critical section is going to release the lock, and that's going to happen, well, again, as each of the processes executes test and set of L, it will cause the copy of the block containing the lock to enter its cache, and it will involve a memory operation, it will involve use of the bus. But sooner or later the process which is inside the critical section will execute the release lock function, which will involve setting L equal to 0, as a result of which L will be 0 in its cache, L will be 0 in the main memory, and all the cached copies of L in other caches will disappear. Subsequently, the first process among the remaining processors which was trying to test and set the lock, let's suppose it's now the third processor in line, executes test and set of L, it will get a copy in its block which will have initially have a value L equal to 0, it will then test and set it, as a result of which L becomes equal to 1 and other cache copies disappear, the main memory copy will become equal to 1, and it can then enter the critical section. Now one can see that the operation of the lock is correct. The cache coherence has correctly ensured that the different processes running on the different processors do not incorrectly update the value of the variable L, which happens to be a lock, and that the mutual exclusion is in fact guaranteed. It was not the case that a process was able to enter a critical section despite not having the lock. The function of the program is entirely correct. But if you think about things more critically, when I had a parallel program in which each of the three processes was executing a while loop in which it was doing test and set of L, which is what was happening in our example, a process running on this processor, process P1, processor P2 and processor P3 were all executing the acquire lock function. And that acquire lock function, they were executing test and set of L repeatedly, a single instruction inside a while loop, and therefore the lock variable was actually going to move from one cache to another cache with each execution of test and set of L on any of the caches, and each of those operations involved a bus transaction and updating of main memory. And this was happening quite frequently, because remember, each of the processes running on the processors P1 through P3 was executing the acquire lock function, in which there was a very small while loop in which it executed test and set of L and then executed test and set of L again until the exit condition was reached. Therefore, if these are processors running at on a 1 gigahertz clock, then they're going to be executing test and set of L many million times I mean, it's going to be executing test and set of L once every 2 or 3 nanoseconds, because the size of that loop is very small. Therefore, the net effect is going to be that if we use this implementation of the lock, acquire lock function, on a shared memory machine in which there are caches, and cache coherence is enforced using a Snoopy invalidate cache coherence protocol like the write once protocol, then we're going to have a new problem that gets created. The problem of the lock actually moving back and forth from cache to cache at a very high frequency. So, as I mentioned, once every few nanoseconds, one or the other of these processors is going to be executing test and set of L as it spins on the busy wait lock loop, and every time any one of them executes test and set of L, the block containing the lock variable is going to move from cache to cache, updating main memory along the way. And this has been referred to by some people as ping-ponging of the lock. You can think of it as ping-ponging in the sense that if you think of the lock as being a ping-pong ball, then it is moving at very high frequency. In the game of table tennis or ping-pong, the ball moves at very high frequency from the two halves of the table. In this case, the lock is going to move at very high frequency from cache to cache among all the caches which are busy waiting on the lock, and hence the term ping-ponging is not inappropriate. It's going to be moving at very high speed. If the players of the table tennis game are very skillful, the table tennis ball moves with very high frequency from side to side. And the net effect is going to be that the performance of the entire computer system is going to suffer. The correctness of the individual programs is not at risk here, because we have seen that the cache coherence protocol is enforcing the correct operation of the lock and the correct access to the shared variables. That's not a problem. But what has been created through this artifact of the cache coherence protocol is that the shared bus and the main memory are going to be kept busy with these test and set instructions. So the bus utilization is going to be extremely high, because once every few nanoseconds, as I just pointed out, conceivably a processor is going to initiate a bus action to update main memory and in its attempt to acquire the lock. Therefore, the bus utilization is going to be so high that the bus is rarely going to be available for any other processor in the system to utilize the bus. And that in effect, even if I had talked about an example in which there was only one process which was doing test and set of L, let's assume that process P2 and process P3 were not doing test and set of L. Even if only process P1 was doing test and set of L, the effect might be as bad. The bus may be fully utilized in just the activity of the busy waiting on the lock by one or two processes. So the primary problem that we have is, we have a situation where we needed locks for the correct implementation of mutual exclusion for the critical sections of the parallel program which is to be executed, and there was a need for a cache coherence protocol in order to ensure that the cached copies of the data, including the locks, did not become invalid or stale. But when you put the two together, you could have a problem that the cache coherence protocol results in a very high bus utilization, leading to the possibility that memory cannot be accessed at all by the other processes running on other processors of the system, or by other programs running on the other processes of the system. And this is a severe problem which affects the system as a whole, as I mentioned. Therefore, in the context of a shared memory multiprocessor with a Snoopy cache coherence protocol, such as the one that we just saw, what should one conclude? One should conclude that this might not be the correct way to implement a lock. By implementing a lock using busy waiting on test and set of L, one is causing a severe problem to the efficient execution of the system. One is not causing a problem for the correctness of the programs running on the system, but there is a problem for the efficient use of the resources of the system, the utilization of the resources of the system. So one has to be thinking about alternative implementations for the acquire lock function in the light of cache coherence protocols. Now, the problem with this particular implementation is that it was a busy wait loop which was busy waiting on the test and set instruction itself. One could actually think of having an implementation of a lock in which the acquire lock function does not busy wait on the test and set instruction, but rather busy waits on the value of the lock. So as long as the value of the lock is equal to 0, it will loop until the value of the lock becomes equal to 1. Now, we saw that this was the beginning of a problem when we tried to implement a lock using this mechanism, because there was a need for an indivisible read, modify, write updating of the lock variable, and that when we tried to implement the lock using a busy waiting on the value of the lock, we ended up with an incorrect implementation of the lock. Now, we can overcome that problem by actually using the test and set instruction to do the updating of the lock. So while we are going to busy wait on a read of the lock, we will actually have an outerlying busy wait loop in which we will busy wait on the test and set of the lock. So we will have a repeat until not test and set of L as the correct, in order to ensure the correct implementation of the lock function itself. Remember, what we are talking about here is how the acquire lock function is going to be implemented. This is the implementation of acquire lock. And the objective of this implementation is to make sure that the busy waiting on the lock is primarily on the lock itself and not on a test and set of L. But realizing that the reason that the lock ping-ponged between the different caches was because we were busy waiting, and in the busy wait operation we were every few nanoseconds testing and setting the lock, which was a modification of the lock. Over here we overcome that problem by busy waiting on the value of the lock and not on an operation where we are modifying the value of the lock. Now sooner or later a process will exit from this loop because L will become equal to 0 when it is reset by another of the processors, and at that point in time it comes to its outer loop where it will attempt to test and set the lock. Remember that there could be many processes, as in our previous example there were 3 or 4 processes, all of whom were trying to acquire the lock. So it could happen that more than one of the processes could notice that L has become equal to 0, but we have the safety mechanism that only one of them will actually observe that it has successfully changed the lock from the value of 0 to the value of 1. The remaining processes will notice that they have changed the value of the lock from 1 to 1 and will continue to go back and busy wait on the read of L. Therefore, this will continue to operate correctly, but will be a little bit better than the previous implementation in that the bulk of the processes will be busy waiting on a read of the lock rather than on a test and set of the lock. Right? And the net effect is going to once again be correct. Of course, there is a minor problem with this implementation in that, as I pointed out, it could be the case that more than one of the processes may notice that the lock has become equal to 0 because they may just execute the check of L at a point in time soon after the point in time at which L has become equal to 0. So for example, it could be that 10 processes all notice that L has become equal to 0 and that all of them try to test and set L. But of course only one of them will successfully test and set L, which is why I say the first one of them to get test and set on the bus wins and will cause invalidation of the other cache copies. But there is a problem with this implementation in that soon after a lock gets released, there will be a lot of bus activity as in this example, 9 or 10 other processes all try to test and set the lock, again using a modify instruction which will cause bus activity. Therefore, one could improve on this particular implementation of the lock even more by setting things up so that once again one is busy waiting on a read of the lock, but rather than immediately allowing, after the lock becomes available, allowing all the processes which observe that the lock has become available to busy wait on test and set of L, which is what we had in the previous implementation, one could actually set things up so that between exiting from this while loop and checking to see whether the lock can be acquired, the different processes could wait for different amounts of time. And this will cause them to actually end up attempting to test and set the lock not at approximately the same time, but at different points in time, and therefore reducing the intensity of the impact on the bus utilization. So as one thinks about things a little bit, one realizes that the implementation of the acquire lock function within a system which is a parallel computer with some kind of a cache coherence protocol along the lines of what we have seen could be a little bit more complicated than the simple implementation of a lock that we had talked about earlier, and that the primary objective would be to try to make sure that the correct operation of the lock is ensured, but in addition to that, the efficient operation of the system as a whole is not compromised. So lock implementations could end up being a little bit more complicated than what we had imagined from our discussion of concurrent programming. This is in the context of parallel machines. Okay, now with this we have a rough idea about what to expect in the different kinds of parallel machines. Remember that there are primarily 2 kinds of parallel machines. There are the shared memory parallel machines and there are the message passing parallel machines. We have seen a little bit about shared memory programming before, in the sense that when we talked about concurrent programming, we were talking about issues such as the need to have mutual exclusion, the need for locks, the need for shared variables, etc. All of these issues related to concurrent programming between processes which had shared variables. They also relate to parallel programs, or maybe talking about parallel programs with threads or processes that have shared variables. And therefore, what remains for us to see is more about the message passing kind of parallel programming. But before getting to that, I'd like to make a few comments about parallel programming in general. Now, you'll recall that when we talked about parallel architecture, I talked about two kinds of classification. One was the classification where we talked about parallel machines as either being good for shared memory types of parallel programming or for message passing types of parallel programming. Before that, we talked about Flynn's classification, in which there was the single instruction stream, multiple data stream kind of parallel machine, and the multiple instruction stream, multiple data stream kind of parallel machine. They differ in that, for example, in the Flynn's SIMD kind of parallel machine, at any given point in time there is one instruction which is being executed by all the processors in the system, or all the ALUs in the system in the examples that I used. Each of them would of course be operating on a different set of data, two different operands. So if there were 1,000 ALUs, each of them could have two different input operands for doing the one operation that they were all doing at a particular point in time, as indicated by their one instruction. And the alternative was the multiple instruction, multiple data kind of a scenario, where we could in fact think of there as being a single program which runs with one process on each of the processors. Alternatively, we could think of it as a piece of hardware on which we could actually have multiple independent programs running on the multiple processors, independent of each other, not cooperating in any fashion whatsoever. Now, given this, one would expect that if one was writing a program to run on an SIMD machine, it would probably be different from the program that one would write to run on an MIMD machine. And it might be good to just talk a little bit about the different kinds of programs, or the different kinds of programming different kinds of programming models that might be involved if at the highest level in thinking about SIMD versus MIMD, for example. Now, the property of the SIMD, I'll remind you again, in an SIMD machine, at any given point in time, there's one instruction which is being executed on all the processors of the parallel machine. And therefore, the program itself is going to have parallelism expressed in terms of the different data which are going to be operated on the different processors by that one instruction. And therefore, one could think about SIMD as having this property of the same program running on each of the processors, but each of the processors using a different piece of data. And one might think about the program in effect as being a single program, multiple data kind of a program. There's the same instruction executing on each of the processors, but they just happen to be using different data. Hence the name single program, multiple data. The alternative is what you might talk of for an MIMD machine, where each of the processors is actually capable of executing a different program, and that you could in fact have a multiple program, multiple data kind of a setup to write programs for a MIMD machine. So one may come across terminologies like this when one comes to parallel programming. Now, in either of these cases, the writing of the programs may involve cooperating activities. And once again, I'm assuming that I'm using the SIMD machine or the MIMD machine. I've written a parallel program, and that the parallel program from now on is something which has a single objective. And I happen to have written the parallel program as multiple processes if I have an MIMD machine. I happen to have written it as these instructions which have separate pieces of data if it's an SIMD machine. But in both cases, it's a parallel program in which there's a need for cooperation between the different parallel activities. We've seen that there are these two main mechanisms for the cooperation, and they were shared memory. And when we talked about concurrent programs, I talked about this as primarily being like it could be threads with shared variables. We can also think about processes with shared variables. Then there was the idea of message passing. And just briefly, we had talked about message passing as being this mode of interaction between processes in which there was explicit communication from one process to the other process using something called a message, which was supported by functions provided by the operating system. Now, in any of these cases, a question which you may ask is, what is the benefit of running the application as a parallel program? Remember that we talked about parallel architecture as potentially giving a performance benefit because it should take less time for a program to execute. Because there's a possibility of having or if there are n processors on the system, I could have n instructions executing at the same time, completing at the same time. And therefore, I could have sufficient improvement in the execution time of the program. So we could actually ask the question, how many times faster could I expect a program to execute on a parallel machine? And the term speed up we had seen when we talked about pipelines. We could also use the term speed up in very much the same way to quantify the extent to which parallel programming might benefit us in terms of how much the execution time of a program might reduce. Now we are essentially going to compute the execution time of the parallel program, which is the benefit that we would get by running the application on a parallel machine. We will compare that execution time with the execution time of a program if it was running on a single processor. And therefore, we will talk about speed up as being the ratio of the amount of time to execute the application as a sequential or a single process program divided by the amount of time that it takes to execute the application as a parallel program. And we expect that the denominator is going to be lower because the execution time should come down if I have written the program to run effectively on the parallel program, and therefore we should have speed ups which are greater than 1. So in general, when we talk about speed up, we are talking about the ratio between the execution time on one processor divided by the execution time on the parallel machine. So the first question which will come to mind is, if I have a parallel machine with n processors on it, what is the maximum possible speed up that I should be able to get? Very clearly, the speed up that I could get is going to depend on how effectively I write the parallel version of the program, how effectively I set up the communication between the parallel activities and so on. But here we are trying to think about the issue of speed up in the limiting sense. Okay, now we are going to assume that I have a situation where I have a processor with, I have a parallel machine with n processors, but let us make some finer assumptions. We realize that if I have a program which was written to run sequentially, it might be the case that I take that sequential program and then modify the sequential program to get a parallel program. In other words, I identify the different activities which can be done in parallel, and then I cause them to execute as separate threads or as separate processes and so on. So one could view the activity as happening in this fashion. You went from a sequential program to the parallel program, and let's suppose that in looking at the sequential program, I realized that there were some parts of the sequential program which just could not be parallelized. There was no scope for more than one activity happening at a time. Let's suppose that I identified that the fraction of the sequential execution time which was of that kind was s. So let me just explain what I mean here. Let's suppose that I looked at a sequential program and I figured out that 10% of the sequential program could not be parallelized at all. Then I might say that s for that parallel program is equal to 10% or 0.1. So we are going to assume that if I analyze the sequential version of the program, I am able to estimate, or I am able to find out what fraction of the sequential execution time cannot be parallelized by understanding of the work that is being done in that region of the program. What this means, of course, is that the remaining 1 minus s, or in this example 90% or 0.9, can be parallelized. Now let me assume that if 1 minus s, or in this example 90% of the parallel program can be parallelized, then I will make the assumption that when I divide that activity across the n processors of the parallel system, I am going to assume that it gets parallelized perfectly. In other words, the time which was 1 minus s will actually get equally divided among the n processors and get parallelized ideally. Now with these two assumptions, I will actually be able to calculate what the speed up could be. Now what is the sequential execution time? The sequential execution time is going to be the sum of the fraction that could not be parallelized plus the fraction that could be parallelized. So that is going to be equal to 1, because here we have reduced the execution times to these two components, each of which is a fraction. The sum of these two fractions is going to be equal to 1. How do I calculate the parallel execution time? The way that I calculate the parallel execution time is, I realize that of the sequential execution time, the fraction which I called s, in this example it was 0.1, could not be parallelized, and therefore in the parallel program this is still going to take the time fraction s. However, the remaining time 1 minus s is going to get perfectly divided across n processors, which means that if I looked at the n processors, each of them would be simultaneously doing the activity which used to take 1 minus s fraction of the sequential execution time, but that is now going to get equally divided among the n processors, and that therefore each of them is going to use 1 minus s divided by n amount of time as a fraction of the original program execution time. Therefore I could calculate the speed up as 1 divided by s plus 1 minus s divided by n, where the denominator is the perfect execution time on a parallel machine, where I could not parallelize this fraction s, but I perfectly parallelize the remaining 1 minus s. Therefore this is the best possible speed up that I could imagine. Now in the ideal case, if I have an infinite number of processors, how much will this speed up amount to? I can calculate that by looking at the limit as n tends to infinity. And what is the limit of this expression as n tends to infinity? As n tends to infinity, this 1 minus s divided by n will tend to 0, and I will be left with 1 divided by s. So this is the answer we were looking for. So if you have a parallel program, if you have a sequential program in which the fraction s of its sequential execution time cannot be parallelized, and then you took the remaining 1 minus s and perfectly parallelized it across an infinite number of processors, then the best speedup that you could get would in fact be 1 divided by s, even if you had an infinite number of processors. And what does this tell us? This tells us that in general the maximum speedup that can be achieved on a parallel machine is limited by the sequential fraction of the sequential program. Remember that s was the sequential fraction. When I looked at the sequential execution time, I figured out that 10% of the sequential execution time could not be parallelized. It is that 10% or 0.1 which determines the best possible speedup that I could get on a perfect parallel machine with an infinite number of processors. This is a somewhat negative result. It tells us that we can, even if we have an infinite number of resources, an infinitely powerful parallel machine, the speedup that we could get would be limited by this fraction. And in effect, if you work out the maximum speedup that I could get for s equal to 0.1, then you'll see that it's a very disappointing speedup of 10. In other words, if I ran this particular parallel program on a machine which has 20,000 processors, the best speedup that I could get would be 10. It could become 10 times as fast as the sequential program, even if I ran it on a parallel machine with 10,000 processors. So this is to some extent to be viewed as a negative result, but it is to be viewed as a realistic way of looking at things. This particular formulation of what speedup might be is known as Amdahl's law, and gives us, it may not actually give us a good idea about what may happen to parallel programs that we write when we write them for parallel machines, because it may be possible for us to improve the way that the sequential program did the work, given that we know that we're going to have to do the same work in a parallel machine, and we may be able to get improved speedups over what this is predicting, because this is working under certain assumptions. But it does tell us that trying to work with as low a fraction of s as possible may be to our benefit. In other words, trying to view the application in such a way that the bulk of it can be parallelized to some extent or the other, rather than being completely unparallelizable. So Amdahl's law allows us to get some kind of a feel for the importance of the sequential part of activity as far as writing a parallel application is concerned. Okay, now our next objective, now that since we know a little bit about programming with shared variables, and I'll remind you that we learned a little bit about programming with shared variables when we talked about concurrent programs. We realized that problems such as the need to look at regions of a parallel program which have shared variables and modify those shared variables as critical sections and ensuring mutual exclusion in those critical sections, the importance of locks, etc., etc. We've learned about that when we talked about concurrent programs, and the principles follow through into parallel programming. We have also seen that while the principles follow through into parallel programming and parallel architecture, the implementation of some of the primitives, such as locks, may have to change. And we saw that in certain kinds of parallel machines, it would not be a good idea to have the same implementation of lock that we assumed for concurrent programming on a machine which has one processor. So we know something about programming with shared memory. We do need to learn something about programming with message passing, which is what we'll proceed to do. So the idea that we understand about message passing is that message passing is some kind of a facility provided by the operating system for explicit communication of data values from one process to another process. Therefore, we suspect that what is needed in order to do parallel programming with message passing is, first of all, we are going to have some kind of a mechanism to create processes to execute on different processors. And we have not talked about this before, but if I have a system in which there are 1,000 processors and I want to run a parallel program which runs as one process on each processor, it may not be convenient for me to assume that I actually initiate the execution of the program on each of those 1,000 processors, because for me to type a.out on each of 1,000 processors is going to take a fairly large amount of time. Therefore, we probably need to assume that a mechanism to create the processes to execute on different processors should be made available. This is not something that we would want to do by hand. Even to execute a program a.out on 1,000 processors may not be convenient for us to do. Now, a second thing that we're going to need is help from the operating system. We need some kind of mechanisms provided by the operating system to send and receive messages. So there has to be a collection of operating system provided mechanisms, one to send a message, one to receive a message. Now we understood that send and receive are the names for the functions provided by the operating system at the sending end to send a message, at the receiving end to receive a message, explicitly from one process to another process. So it seems obvious that the identity of the communicating processes must be explicitly specified, and that in the send function it must be possible to specify which process one wants the message to be sent to. As a simple example, it's possible that the operating system sets things up so that we refer to the processes by their process IDs. We know that in Linux or Unix systems, each process has a process ID, which is a small integer, and each process on a system will currently have a unique ID. So it's possible that process ID of the one process is 13 and the process ID of another process is 15, and I'm referring to those as P1 and P2 here, but here we're talking about small integers. Now in general, this may have been okay for assumption on a system where there's a single operating system and a single processor, but remember now that we're talking about a situation where we have multiple processors, and it's conceivable that we need to view this as, for example, a situation where there is Linux running on each of those processors. And therefore it no longer makes complete sense to talk about the process ID as the Linux process ID associated with the process. Why? Because I could have a situation where process 13 running on processor 1 has to communicate with process 13 running on processor 3, and that therefore just thinking of the process ID as being the Linux process ID may not generalize anymore. We may need to have something a little bit more complicated than that. For the moment, I'll just assume that we have that mechanism, the mechanism by which we can identify communicating processes uniquely on any processor of the system. But we expect that what the send function or the send system call, whatever it may be, is going to look like is something like this. And process P1, if it wants to send a piece of data to process P2, will use send. It must explicitly specify that it wants to send it to P2, and it must explicitly mention the data. In this particular example, it has put the value into a variable called x, and the address of the variable x is what is used by the send function or the send system call. Now at the receiving end, I'm also assuming that the process P2, which is expecting to receive a value from process P1, must explicitly execute a receive function or receive system call, depending on what it is, in which it explicitly mentions that it wishes to receive a message from process P1. Why is it necessary for process P2 to explicitly mention that it wants to receive a message from process P1? Now the way to view this is that in general, when we write parallel programs using message passing, there could be more than two processes communicating, and it could be that there's a need for process P1 to communicate to process P2, and that possibly maybe as another part of the activity of the parallel program for process P3 to communicate with process P2. Therefore, within process P2 there are going to be separate calls, one for the receive from process P1 and one for the receive from process P2, and therefore it seems necessary to actually have in each of these two calls, in order to distinguish one from the other, explicit mention of which was the sender from which the message is expected. Once again, the data from process that was sent by process P1 will be received as an activity of the receive function execution and will be put into a variable of process P2. So y is a declared variable of process P2, and the address of y is what is passed as a parameter to the receive function. So you notice that this is a setup for communication between process P1 and process P2, in which there are no shared variables between process P1 and process P2. All that is necessary is a mechanism for sending and receiving messages between processes, and some mechanism for creating these processes on different processors. In addition to that, mechanism to specify the identity of another process. Process P1 identifying process P2 as its communication partner, and process P2 identifying process P1 as its communication partner. Now, different operating systems will provide support for message passing with different sets of functions, and therefore it's a little difficult for us to understand how we could write a parallel program which is going to run on, let's say, 1,000 processors, in which some of the processors might be running one version of Linux, some of the other processors might be running some other version of Unix, and so on, and might be more productive for us to try to think about a mechanism which is abstracted out above the operating system. And that's what we'll assume. We'll assume that in doing message passing programming, we might not be using the operating system provided functions directly, such as this send and this receive, which I've been talking about, but rather we might use some kind of a library which will make the appropriate operating system calls as part of its activity, but will make it unnecessary for the programmer to have to know about the nature of the operating system support for message passing on each of the different variants of Linux or each of the different variants of Unix that the parallel program may have to run on. And therefore, we expect that there is going to be some kind of this abstraction provided by a library. And if one looks back in time, one will find out that at different points in the history of message passing, people have created new libraries for this purpose. If you look back into the 1980s, there was a library which was known as PVM, or Parallel Virtual Machine, which used to be fairly popular. Since the 90s, the dominant message passing library has been something called MPI, and the library was created sometime in the 90s and continues to be a widely used library for message passing programming. And we will therefore proceed to talk about message passing programming in the light of MPI. Okay. So I'm going to use MPI as the example of how one can do message passing programming. You will find out that it is widely supported on almost any parallel system that you could talk about. If not, one can download the MPI libraries and cause them to be installed on the parallel systems which you are dealing with, and write message passing programs using MPI. In terms of references, I've given you two good references to learn a lot about MPI. Both of them are available through the URLs which are provided. The second is a book which can be downloaded or chapter by chapter referred to across the internet. Okay, now first of all, let me mention that MPI stands for Message Passing Interface, not a surprising name for a library that is primarily intended for writing message passing programs, parallel programs. But in effect, like any other library or interface, it provides a standard application programmer interface for doing message passing on systems regardless of how the operating system may actually support the send and receive functionalities. So in effect, the MPI hides the hardware and software details of the underlying parallel machine. It's no longer necessary for the programmer to worry about what functions are available on the version of Linux or the version of Unix that the parallel machine happens to be running. In fact, the programmer need not be aware of the hardware details or the software details. This makes MPI programs portable, in that you could write a parallel application using MPI message passing and run it on one particular parallel machine. You could then take the same MPI program and run it on a cluster of workstations and expect it to run correctly on the cluster of workstations. So the portability is good because of the fact that it hides the hardware and software details. There's also some flexibility which results. Now, as I mentioned, MPI is implemented as a library. It's a collection of functions, it's a collection of include files, and the implementation of the functions which constitute the application programmer interface. From the perspective of your program, once you write an MPI program, so your program that I'm talking about over here is an MPI program that you have written. In other words, the assumption is that you have written a parallel program which is going to run as a collection of processes, and the processes are going to be communicating with each other using message passing in order to achieve the common objective, and that this is going to be done using the MPI message passing interface functions, not using the operating system provided functions directly. So as far as your program is concerned, your program is the topmost box over here. Your program is written to use the MPI library. Now, again, depending on what system you are running your program on, the MPI library may make use of some standard networking functionalities, such as TCP/IP functionalities, and it could be making assumptions about some standard network hardware. That's one possibility of what the setup could be on the parallel machine that you are dealing with. The other possibility is that there could be some custom software, some handcrafted networking functionalities, send and receive functionalities that were created for the system that you're dealing with. That would be called custom software, which was necessary because the hardware was also specially designed for that particular system. But as far as you as a programmer are concerned, you just have to know how to deal with MPI, and then the implementation of MPI would be suitably selected by the person who constructed the system to be such that it used the correct version of the MPI library, and therefore your program can be written in this portable, flexible framework. Now, as far as we're concerned, MPI can then be viewed as a collection of functions. library of functions. And let me just show you some of the key MPI functions and constants before we actually go ahead and talk about MPI itself in more detail. I'm doing this just to demystify MPI. You'll recall that when we talked about system calls, I told you that the system call is this very special kind of a part of the operating system, and it is part of the operating system and must be dealt with great respect. One cannot expect that one can execute system calls and modify system calls, but rather I got into it by telling you the names of some of the system calls, and you realize that you had actually used some of those functionalities before in some of your own programs. For the same reason, I'm just going to mention some of the MPI functions, and then we'll see that it's going to be quite easy to write simple MPI programs. Okay, now the first MPI function that any MPI programmer has to know about is MPI init. And as the name suggests, MPI init is a function which must be called once at the beginning of the MPI program to initialize the various activities of the MPI library. By the same token, you'd expect that at the end of the MPI program, there's going to be a need to wrap up the various MPI activities, possibly, and therefore there's going to be a function called MPI finalize, which must be one of the last things that must be called within the MPI program. You suspect that somewhere in between there's going to be activity of causing processes to run on the different processors of the parallel machine, etc., and that and the communication between those processes. But one would expect to see MPI init at the beginning of the MPI program and MPI finalize towards the end of the MPI program. Now, one of the concepts about MPI that we're going to learn about later is this concept of rank, which will abstract out the notion of the process ID. So rather than talking about the ID of a process from the perspective of the Linux process ID associated with that particular process, we abstract things out into something called an MPI rank, and the number of processes that the program is running as will be known as the size, and there are functions to determine what the MPI rank of a particular process is, and the process can find out its own rank by calling the MPI function MPI_com_rank. I'll mention a little bit more about this later. Similarly, by calling the function MPI_com_size, any given process of the MPI program can determine how many processes there are in this particular MPI program, or how many processes this particular MPI program is running as. We expect that there are going to be functionalities in MPI for sending and receiving messages, and they go by the names MPI send and MPI receive. There are actually families of functions. I'm just showing you a representative example, MPI_send. You'll notice that each of the MPI functions identifies itself by starting with MPI_, and you'll notice that there are various parameters to send, various parameters to receive, which we will have to learn more about. There are several other MPI functions, but I talked about the fact that there are certain MPI constants, and the MPI constants once again are declared constants which are available in the MPI library, and all start with MPI_, and you'll notice that there are some which seem to be used to specify types. For example, MPI_char is a constant which seems to be used to indicate that a particular variable is of type character. Similarly, there's int, long, and byte. And then these two mysterious other constants called MPI_any_source and MPI_any_tag, which we need to understand more about. So basically, the MPI interface is a collection of functions and a collection of constants, and once one has understood all the functions and all the constants, one can readily write MPI programs, which means that one can write parallel programs which use message passing for the communication and interaction between the processes, allowing them to achieve their common objective. In the lecture to follow, we will look at the MPI functions in more detail. We'll understand how they can be used. Then we'll look at some examples of writing applications as parallel programs using message passing as their mechanism for interaction. We'll stop here for today and look at MPI in more detail in the lectures to follow. Thank you.